Okay, so just to make sure, you see my screen and you see the mouse.
Yeah.
Okay, great. So let's go.
Okay, so thank you everyone who's here. This is the last seminar of this season, so it's a nice way of closing up. Ylann approached me to ask for to give a talk, and I think it's a very good thing. He is a master's student that is finishing his project, his master's project in his master's is in EPFL, but he's doing like a long stay here. And I think speaking with him, he's in the process of starting his PhD, which is a very good thing. So let's welcome Ylann.
Okay, thanks. So so that's the last seminar. I saw that the first one also was about defects and topological defects in active matter. So that's quite good symmetry to see. So as you said, I finished my master's project with Demian Levis on this particular topic. So the name is Defect Superdiffusion and Unbinding in an Active 2D XY Model. So okay, so the title may seem complex, but basically in one sentence, what we do is that we study the collective motion of some structures that we call topological defects. And we study specifically the difference between the collective motion in equilibrium and in active system. Okay, so what makes this problem, let's say, interesting, motivating? Is okay, we'll gather in what follows three main ingredients, namely we have a two-dimensional system, we have short-range interaction between our particles, our spins, and we have continuous symmetry, namely we have a continuous variable, you can think. And when you have these three ingredients, at least in equilibrium, you have a very well-known theorem, that is the Mermin-Wagner theorem, that basically states that you can have no long-range order, at least at finite temperature. And this, before 1973, meant that you couldn't have any phase transition. And in 1973, these two guys, Kosterlitz and Thouless, came up with this very brilliant idea. They actually claimed, okay, this Mermin-Wagner theorem is true, that's a mathematical theorem, but there is actually a phase transition that we just discovered. It's a topological phase transition in the sense that this transition is driven by the collective behavior of topological defects. So if you're not very familiar with this concept of topological phase transition, vortices, topological defects, etc., that's no problem, because I will try to explain in simple words what they are. And topological defects, okay, you can define them in several ways depending on what area of physics you work in, etc. But for what is of interest today, let's say, topological defects are these two. So on the left, you have what we call a vortex, on the right, an anti-vortex. So these are particular structures that you can visually identify quite easily. If you have a field of arrows, always pointing up, for instance, if you have these specific structures, that's what we call a topological defect. And when a vortex meets an anti-vortex, they basically annihilate, and you get back, a plane field all pointing up, for instance. So let's keep a bit visualizing what a vortex is and what it actually means visually. So in this system, like 32 by 32 system, which is very small, but just for you to visualize, you can immediately see that you have two vortices, namely one vortex here and one anti-vortex. And if these two actually collide, they annihilate, as I said, and leaving the field with a complete ordered phase. Right, and what I will do in this presentation is basically, I cannot represent arrows. I will represent the angle, the phase of the arrows with a cyclic color scale like this. And if you do this, you immediately identify the vortices, with these two characteristic signatures with all the colors in one point. So this is what we call a vortex today, let's say. Okay, so what am I talking about? Topological defects, and okay, what is the system that can actually helps us understand how they behave? This system, this model has been, well, is the two-dimensional XY model. So maybe you've heard about it. I will just introduce a bit what it means, so that everyone understands actually what that takes later on. So this is a very simple model, let's say conceptually at least. So it is a two-dimensional model. It's a lattice model, meaning you have all the particles or the spins that you wish that are pinned to the lattice. It's a square lattice, so every spin has 4 neighbors, and the only thing that it can do, actually, they cannot move. The only thing that can do is actually fluctuate. The phase theta here can fluctuate. And so this phase theta is ruled by this equation of motion, which is a overdamped Langevin equation. And it has 2 terms, basically, and I will explain this in a second. So the first term is an alignment term that promotes local alignment and local ferromagnetic alignment with the 4 nearest neighbors. So basically, if you have, I don't know if you see my hands, but basically, do you see them?
No.
Okay, well, imagine you have 2 spins, one pointing up and the other pointing upright, for instance. They will tend to align because of this interaction, non-linearity interaction. So this promotes local ordering, and on the other side you have the classic thermal noise term, which is a Gaussian white noise, and this, on the contrary, will promote disalignment, disorder. So this you have a competition between ordering terms and disorder and noise, basically, and this will naturally no, but this will set up a transition that we call the Berezinski-Kosterlitz-Thalers-BKT transition. So this transition is a transition from at high temperature you have a classical disordered phase with exponential correlations, and if you go below a certain critical threshold, the critical temperature, in this case is numerically equal to .9, basically. If you go below this temperature, you enter the low temperature quasi-ordered phase, right? So it cannot be a real long-range order phase because of the Mermin-Wagner theorem, but here we have what we call a quasi-ordered phase, and that's what's very interesting in this phase transition. You have, space correlation that decay in a parallel manner, meaning that it's extremely slow, so you can still have order, let's say, on very long length scales. So now this is like a transition, but as I said, this is driven by this is a topological phase transition. So it means that it's driven by the collective motion of vortices, of the topological defects. Okay, so in the low temperature phase, the vortices I've shown are bounded, meaning that a vortex comes in pair with an anti-vortex. So they're basically bounded, meaning that they attract each other, they interact in such a way that their influence, which normally would span the entire system, actually when you have 2 vortices that are bounded, the influence is only local, let's say, that actually spans on the scale that is the scale of the pair, the pair separation. Okay, so when you have bounded vortices, you have this quasi-ordered phase coming on. And if you rise temperature, if you get above the critical threshold, these vortices basically unbind, and as I said, their influence actually spans the whole system. This is why you enter the disordered phase. Okay, so what's going on here? So this, so you still see my screen, right? Because there was a new window opening. Okay, I think yes.
Yeah,
okay,
you're good.
Okay, so this transition actually applies for many different 2D systems. I only name a few, like liquid crystals that you actually, liquid crystals, the true transition of melting, also superfluid, etc. All these systems actually fall into the class of universality described by, this BKT transition. So now the question is this BKT scenario still valid for active system? Because I've only talked about equilibrium systems so far. And the thing is, we don't know, well, at least we didn't before this work, how the BKT scenario was affected by, if you put activity at the particle level into the system. So equivalently, the question is, how are the topological defects affected by this local input of energy? Maybe I can stop here for a second so that I make sure that everything's clear. If you have questions, maybe it's the time to raise them, if everything was really unclear or not. No? Okay. So before actually entering the answer we gave to it, I'd like to speak a bit of the spirit of our answer. We actually focus on the very fundamental concept of unbinding, the core mechanism of the BK transition, and we don't want to address a particular specific active system model, right? Like you could think of pneumatics, etc. We actually want to focus on the fundamental concept, and this is why we come back to the roots, back to the basics, basically. So we basically add activity to the XY model I just presented you to get an active XY model, and in this framework, which is well controlled because we know the limits are well controlled in the absence of activity, we will try to answer the questions above. Okay, so to do so, as I said, we want an active XY model, and to do so, yes, we just gather the very same ingredients as before. So we still have 2D system, we still have a lattice. The spins actually don't move spatially. We still have local interactions, continuous spins, etc. The only thing that actually changes is the very equation of motion of each spin. So it has 3 terms. 2 of them you already seen before, and the only thing that actually changes is the first one. So we call this term the driving term. We also call this the intrinsic frequency of the spin I. And I'll just give you a taste of what it makes. So basically, if this red term would be 2, for instance, I just invent out, it means that the spin I will want to rotate at 2 revolution per second, right? 2 hertz. If it would be -1, it would be okay. Minus like 1 revolution in the counterclockwise, in the clockwise direction. So it's basically a driving we impose on the spin I, and since every single driving for every single spin is independently, drawn from a Gaussian distribution, it makes not only the system out of equilibrium, but also active, because every single spin is individually and independently driven. Because that's a very important detail, because it actually puts our framework into the framework of active systems. So now let's just explain a bit what physical system can this equation actually model. So it is close to what we call the Kuramoto model, and this Kuramoto model is the simplest model, let's say, to explain synchronization phenomena. And I'll just show you one so that you have an idea of what this actually physically represents. This is the synchronization of metronomes. So let's say we have our 32 metronomes, or say 32 spins. These are all different, meaning that they all have an intrinsic frequency. One would like, for instance, to beat at 3 per second, the other one 2.5 per second, and so on and so on. So we launch them individually, and this is why in the beginning, okay, does it work? Yeah. They just beat completely randomly. Nothing is actually synchronized in time. And if you wait long enough, you see that it actually starts to synchronize. And if you wait a bit longer again, you see that under the influence of this term, basically, the synchronizing term, they all beat synchronously. Okay, so for the little story, you can see that, you know, the table moves from left to right to left to right to left to right. And this movement is actually the key for the synchronization. It means that every metronome will be affected by this, you know, shearing motion, and it makes every single metronome communicating with every other one. Okay, so this is not, for this particular video, this is not a short range Kuramoto model. This is the actual original Kuramoto model, but still you have the namely long range Kuramoto model. But still you have the idea of what kind of physical system you can represent with, you know, this kind of equation of motion. Okay, so let's go on. So to recap, we have a model that actually describes a local, noisy, two-dimensional synchronization phenomena. And to control it, we have two control parameters, the noise, thermal noise, and the strength of disorder sigma. Right. So for historical reason, we actually work with sigma squared, but that doesn't change anything. Okay, so I'll recall the question: is the BKT scenario still valid for active systems? And the answer I'll detail in 3 parts. Okay, so what time do you have? Okay, perfect. First of all, I'll go into a very simple observation, like picture the system so that you have a global taste of what's happening. And then I'll enter, you know, the study of the behavior of 2 vortices, and then I'll address the behavior of 1 vortex and the statistic of its displacement. Okay, so first observation. So here you have 2 systems, 2D lattice, 200 by 200. Every single pixel is a spin, and every single spin has a color. The color denotes its phase, its angle, from 0 to 2 pi on a color scale, which is cyclic. And you can see that for this particular typical realization, which is at low temperature, below the critical temperature, you have what I told you about. You have bounded vortices, namely that this anti-vortex and this vortex, you can basically say that they are linked together because you can, by eye, pair them with the field lines, same for these 2. And you also have the quasi-long-range order I mentioned, namely that, you know, on scales that are close to the scale of the system, you have the same color, basically. I mean, it means you have long-range, like quasi-long-range order. On the right, you have the active XY model. So this is the very same temperature. The only thing that actually changes is here we have disorder, here we didn't have. So this is equilibrium, this is activity. And here you can already by eye say that everything is completely different. We have let's say a new physics. So looking back, we will see that actually this picture already has a lot of information in it, but for now I'll just make 2 statements. The first one is that in opposition to this picture, you can say that you have a very finite characteristic length scale here. You have, you know, a fine structure in the system. So this we'll address quantitatively in a second. And the other thing that we'll see later on in this presentation is that you can no longer, you know, pair the vortices by eye. You can no longer say that this vortex is paired to this one, or to this one, or to neither of them, etc. So this, as we'll see later, is actually true. You can no longer pair these 2 because the vortices, as we'll see later, are completely dynamically free. Right? They're not bounded anymore. Okay, so now let's go. So we talked about characteristic length. So let's say, let's quantify this. So to do so, we actually look at the spatial correlation function, which is defined, you know, very typically in this way. And here it's plotted on the log-log scale. So log-log scale means if you have a straight line, this is a power law. If you have curved line like this is like you have a geometrical decay, and in this case, these are exponentially decaying functions. So what do we learn of this from this? Well, this blue curve is the equilibrium case. So sigma is equal to 0. This is the traditional XY model, let's say. And you can see that we do recover. This is the same curve here, but zoomed in, let's say. we do recover the very power decay with the right exponent from the literature, etc. So this is the left picture here. The right picture here is described for different strength of the disorder sigma squared. Here, and if you increase the strength of the disorder, you go this way, right, from orange to brown, let's say. So what we learn from this picture is like the qualitative way of decaying changes absolutely. You go from power law to exponential, meaning that you go from a quasi-ordered phase to an actual disordered phase. From this exponential, because they are exponential, you can define this way a characteristic length scale, right? So I mean, if you hit, as soon as you hit 1/e, which is basically 0.3 uptake, you go down, and this is your characteristic length scale psi, right? So, and then we report this characteristic length scale with the disorder, against the disorder. And you see that, if you're interested, I'll come back to this in the discussion after, but we see that independently of the system size, we have like a very clear, very clear scaling, namely that we have the length scale that is scaling as 1/sigma. Again, this we understood analytically, but since that's not the main idea of the talk, I will keep it for later if I have time. Okay, so these were the first observation, pictures, quantitative, and now I'll tackle the behavior of the pair of vortices. So first, before entering actually, curves and graphs, I'll just show you videos. On the left, you have the equilibrium XY model. So we basically created this lattice with two defaults. So you have +1 default and a vortex, and here you have a -1, an anti-vortex. And if you let the system evolve in such condition that you have, well, at low temperature, let's say, so you don't have many spontaneous creation of defects, you see the following. These two vortices just attract each other, and eventually they will annihilate, and leaving the entire system ordered, let's say, because there's no topological defects anymore. So okay, what you have to keep in mind is that they attract each other and eventually they annihilate because of the attracting force. On the contrary, if you have the system with the same temperature but a bit of disorder, and that's only a bit, trust me, what you see is completely different. So you have the same initial distance between the vortices, but you see that the future trajectories here, plotted here and plotted here, will actually look completely different from this one. Okay, I'll show you the video and then we comment it. Okay, so what you see basically is that these vortices live basically their life independently from each other, right? They do not attract anymore, and they basically, live their life independently. So that's, very important because, as I said, the BKT core mechanism is that vortices are bounded below a certain temperature. And here you can see that at the same temperature, if you add disorder, you do not have this binding phenomena anymore. So this means that dynamically the vortices, the defects, are completely free, right? So it kills the BKT core mechanism. What can I say also, and this we'll tackle later, is that, this trajectory is very reminiscent of, diffusive one with an attractive potential. On the contrary, this one is no longer diffusive, right? It is completely superdiffusive, and we'll actually tackle this the superdiffusion in the third part of the talk. Okay. So now, quantitatively, we actually see the very same thing. On the left, you have the separation distance between the two vortices against time. You see that for equilibrium cases, like the plane curves, you have, as expected, a decrease, right, in the distance over time. This is because they attract each other and eventually they bump into each other, so they annihilate. The dashes are the theoretical prediction. So you see that we do match very well the theoretical prediction. And if you're interested in why the actual curves deviate from the prediction, we can talk about this in the end. This is nothing else but a numerical artifact. Okay, so this was the equilibrium case. You have separation that decay that decay until zero, basically. As soon as you activate the system, you see that the separations basically remain rather constant. This is the initial separation, and it basically remains at 30 at all times with a bit of fluctuations, but still. And this is because, as we saw just before, the vortices are free, right? So they no longer attract. They don't see each other. So basically, they have one half of chance of probability to go into the same direction and one half to go separate, right? So in average, the average separation distance remains constant, right? So that's another signature of the freeness, let's say, the freedom of these topological defects. And we can see that this does not depend on the initial separation, because whatever parameter you choose for temperature, for disorder, whatever the initial distance you have, you basically end up on the x equals y line, right? Meaning that you remain basically constant over time. Okay, so we saw that vortices are always free and they only meet, thus annihilate, by pure chance, right? Okay, so now, as we saw that vortices are free, so you can basically no longer consider them by two. We'll see what happens for one vortex, and we'll study the vortices displacement statistics. All right, so a bit, simple word on the method we used. So everything again is numerical, and we create a very big system with one vortex at its center. We let the system evolve, and we make sure that there's no spontaneous defects creation, because we want to track the vortex over time so that we have the position as a function of time. So this is an example for a very small system. I guess that you just visualize what's going on. Why do we take a very big system? We take like 400 times 400 system. Is because if you only have one vortex, you can no longer ensure the periodic boundary conditions. And we were initially afraid that the border effects will actually affect the vortex, which is in the end not the case, because, as we said, vortices don't see each other. It means that you have like sort of a screening effect. They don't see very far in the system. So eventually we could have done this with much smaller systems anyway. So what we see, first at equilibrium, so that we could recover the well-known results. We see that the G of xt, which is the PDF of displacement, so the probability to be at position x at time t, follows a simple diffusion PDF. So okay, so this is the PDF for different times. So small times on the left, and you go right, you have large times. Just to prove you that this scaling is is correct, you can renormalize the axis like this, and you see that all these curves actually collapse on one master curve. So we do prove that this scaling is the good one. So just to say how we got the scaling, we actually made the usual scaling hypothesis, namely that this J of xt actually follows, the x divided by some function of t, and we see that if you have this scaling hypothesis, a simple Gaussian will fit very well the data as we see here. Okay, so physically, what does it mean? It means that the mean square displacement that we see here, which is basically the denominator of this fraction, is diffusive. So the mean square displacement follows simply t, follows t with a logarithmic correction. So this can be understood. There's one paper in the literature that already tackled this problem, and we recover the same, result. So physically, this means that if you have a single vortex here with only temperature and no disorder sigma, it basically wanders around like this, diffusively, let's say. On the contrary, if you activate the system, so you put some sigma, you still have the same global form, as you can see here, but very importantly, the mean square displacement is no longer diffusive. So before we had t to the power 1, here we have t to the power 3/2. So this means that the vortices super diffuse, and this is what we saw in the movies, right? So yeah, maybe I can go back to the movie so that we, this. Here you see the typical trajectories, right? So by AI, you can already say that they are no longer diffusive, and the coefficient, the exponent 3/2, actually describes, this kind of trajectory. So it's not ballistic, it's not diffusive, it's in between. You have something that is super diffusive due to the activity that we put in the system. Okay, so what can I say more? How much time do I have? Okay, I have a bit of time. Okay, let's go back. So there we were. It's freezing. So maybe to sum up the take-home message before we actually go into the discussion. In the active 2D-XY model, we saw that the vortices behavior is completely modified with respect to the equilibrium case. We saw that they are unbounded, they completely become free, and so the BKT scenario is no longer valid. So we actually answered this open question for the very first time. And we also saw that vortices, active vortices, super diffuse with Gaussian statistics. Namely, we have the mean square displacement here, scaling like t to the 3/2. Okay, and what's very interesting is that with this very simple model, I mean, it's only it's quite easy to numerically simulate, etc. You have only 2 control parameters. It's well controlled. We have limit case is well understood. So it's very simple, and yet it reproduces feature of very recent experimental setups that were conducted by Denis Bartolo, namely these 2. Okay, so I'll just briefly touch a word on these 2. So these are active systems. For the case of this paper, Ylann and co-workers, you have magnetic colloids spun by an external magnetic field. You have hydrodynamics interaction, etc. And still, you recover the grain boundaries we saw in the movies. You still see that the characteristic length scale psi decreases as you drive the system far away from equilibrium, and you also see superdiffusion of particles with the same exponent 3/2. On the other hand, this paper also by the team of Denis Bartolo has another different setup, which is colloidal rollers spun by the Quincke mechanism. And they also see that, you can see, so all these are, vortices, plus and minus 1 vortices. And you see that these vortices actually self-organize onto grain boundaries also. Here you also have, pressure and hydrodynamic features, let's say. But still, you see that the vortices self-organize onto grain boundaries. The vortices can eat the boundaries as they slide on them, etc. So what I want to tell with this slide is basically a very simple model actually reproduces features of actual experiments. So we have high hopes of touching some universal features, universal rules and mechanism of active system with this very controlled, let's say, platform to investigate active system. So yeah, with this, I thank you for your attention, and I'm open to questions if you have some.
Thank you very much. Are there any questions? Yeah, Ido.
Hi. Thanks.
Hi.
Thanks for the nice talk. I wanted to ask you. You refer to these patterns that you observe with the activity as completely disordered, and for some reason, to me, it's not very reminiscent of the classical disordered phase that you get in equilibrium. And I'm wondering, like, these patterns that we see I see like stripe patterns, and the stripe pattern itself seems to be at the length scale of the system. So maybe if you look at the correlation of the order, then you see the decay, but there are some patterns here that seem to be large. So any thoughts on that?
So you mean these patterns, right?
Yeah.
Okay, so these patterns, okay, I do have a thought, and then you tell me what you think about it. Basically, if you see, if you quench the system from a very high temperature, you see that initially the classical XY model physics is at stake in the beginning because you don't have these these structures.
Mm-hmm.
It means that you have some coarsening of the domains, as in the XY model, and as soon as you have coarsening, it means that you have, for instance, you still don't see me, right? My hands.
Yeah.
Yeah, you do. Okay. So you have, for instance, a domain here and a domain there, like pointing in different directions. And as they grow up, they will eventually meet, and the barrier, the frontier, let's say, will actually result in this domain.
Mm-hmm.
So this is why eventually you have like spanning, system size spanning domain. So now the question was, is this a real disordered state? It is a disorder. I meant disorder in the sense that if you look, as you said, if you look at spin-spin correlation, it decays exponentially fast. I don't know if you could, so the final word is this, I don't know if you could investigate, if you can get order out of these patterns. I'm not sure though.
Okay. So is there, what is the role of temperature in the active case? Is there some critical temperature, or is temperature just irrelevant?
For the unbinding mechanism, the temperature is not relevant, but it does have a very specific role. Namely, if you look at this, you have what we call the pseudo diffusion coefficient, and this diffusion coefficient, which actually determines the speed, the velocity of the defects, only depends on temperature in this way, right? So you have
the velocity of the defects, I understand, but if you would take a snapshot at low temperature and high temperature at your pattern, will it look qualitatively different?
Qualitatively, no.
Okay.
You still have the same thing, yeah.
Okay, thank you.
Sure.
Carla.
Hi, Ylann, very nice talk. I wanted to ask you about so this mean square displacement that you see in first in the equilibrium case. What's the reason for this scaling or this logarithm of time in the denominator?
Okay. This actually come from the fact that the motility of the defect is affected. I can't really remember the actual mechanism, but this comes from the fact that the motility actually has a log in it, a log correction in it, so it propagates throughout the computations until this.
Okay.
I cannot be more precise at the moment. Sorry.
All right. Yeah. And about the active case where you see this exponent of 3/2, does this depend on the, so if you run longer simulations, does this stay like this, or is this
coming back to diffusive?
Yeah.
Okay, so that was a big debate with Damien at the time. We were actually surprised to see that even if you push, we did 10 times for one curve, we did 10 times the maximum time, and it actually still is 3/2, like plainly 3/2. We don't see any behavior going back to diffusive. We don't actually really understand why this is the case, like quantitatively speaking, but maybe I can explain a bit. The superdiffusion comes from. Sorry. Wait a second. I want to show you the movie once more so that I can explain what how the boundary plays a role. Mm-hmm. Okay, so there we go. Okay, you see that the boundary here actually corresponds to the future trajectory, right? So you see that within a very small space interval, you have all the colors, meaning this is a grain boundary, let's say, between two domains. Look at the boundaries below the vortex, right? And you see that the boundary is eaten by the vortex as it like a zip, let's say. Okay. So do you see what I'm talking about?
Yeah.
Okay. So this is hand-wavingly, let's say, the cause why there is actually superdiffusion. There is a preferred direction, namely here, because there is more energy. Let's say you have. I can show you later that the energy of the system is concentrated into these boundaries. Okay. And so, as long as you have boundaries, you will have superdiffusion. You will have your 3/2. And what you see is actually, so not on the scale of one trajectory, but you see that these boundaries are erased by the vortices and are created at other places in the system. So basically, as long as you have this creation in time, you will have support for your superdiffusion, and hence the 3/2 will never go back to diffusion, right? Did I answer your question?
Yes, I mean, yeah. Okay, and then I have a third question. So in the active case, you see that there's no binding between the two vortices, but what if there's what if they collide by just by chance?
They can collide by chance. They can actually, and in this case, it's just like if you had equilibrium XY model. They just annihilate if there's a plus and a minus one.
Okay.
But this is by pure chance. You don't have a global mechanism that promotes this annihilation.
Mm-hmm, mm-hmm. But so you've seen those events of.
Yes, but they're quite rare. They're not common, let's say.
Mm-hmm. Okay.
But they do happen.
Okay. Okay. Cool. Thank you.
You're welcome.
I think Gio has a question. I don't know if Ido has another question, but maybe Gio can go first.
Sure, thanks. Nice talk. So this is in connection with the previous question. So regarding the creation and annihilation, so here you have shown the videos for the active case say temperature 0.1 and 0.1, and you mentioned the temperature doesn't have an effect beyond the, say, the velocity. So, but when you increase the activity parameter here, I mean, the natural case in active systems is that when you increase the activity, the number of the defect density also increases. So is it similar in this system as well?
Yes, we do have this. Okay. So in all these videos and all the graph, as we wanted to track the defect, we actually want to limit the number of vortices. So we place ourselves in conditions under which you have the smallest possible probability of spontaneous creation. But as you said, if you do increase the activity or the temperature, you can enter a phase where you have more vortices. All right. So the colors here are the number of vortices. Let's say the number of free vortices with another criterion, which is a geometric criterion. I can tell you a word on this. But basically, if you increase temperature and or activity, you end up having loads of vortices, and this actually increases exponentially with temperature, for instance.
Okay, and this, I assume, will be in keeping in conserving the topological charge, right? But they always get created in pairs. If
you have a periodic boundary condition, yes, of course.
Yeah.
If you do not, that's a completely different mess.
Yeah. So in the event of multiple defects, I don't know what could be the threshold. Say you have a sufficiently high enough sigma square or T. And then in that event, would you expect that the trajectories would still be super diffusive?
I think yes, because there's no reason, I can't see any reason why you don't have this, but there will be super diffusive on a short time and short length, because they will immediately counter another one, right? So it's very it's very difficult to measure, but I think that qualitatively there's no reason why it shouldn't be super diffusive.
Okay, thank you.
Sure. There was another question, I guess, man.
No, I think that's everything. So thank you very much, Ylann.
Yeah,
very nice
welcome.
talk. And thank you very much, everyone else, for coming. We'll see each other the next seminar next year.
Okay.
Bye.
Thank you very much.
Thanks.
Bye. Thank you.